Chapter 6, we're looking at random variables in 6.1, 6.2, and 6.3. We're going to have a series of videos here that looks at how do we find probabilities for random variables. So in this first video, we're going to be talking about mostly discrete random variables, and we're going to be looking at how to calculate the mean and standard deviation for these things. So first, let's talk about some basic terms, some big ideas that are going to be overarching in these sections. So a probability model, we've seen this, it describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. We've seen those in tables quite frequently. A numerical variable that describes the outcomes is called a random variable. The probability model for a random variable is called a probability distribution. So here's the big definition box, basically says the same thing as above it. Here's an example. We're going to toss a fair coin 3 times. X is our random variable. X is representative of the number of heads obtained. So the possible outcomes for X, the possible values it could take on are 0, 1, 2, or 3. And we have the sample space listed here. And here is our probability distribution in table form. We have our possible values for the random variable across the top and each corresponding probability in the next row. We can also create histograms for this. And because each bar of the histogram is representing a single value, we can center the bar on top of that value. So this bar that's centered on 0 represents getting 0. Bar that's centered on 1 represents getting 1, and the probability is going on our vertical scale. So 2 types of random variables. We've seen these terms before, discrete and continuous random variables. Discrete are countable, continuous is measurable. A discrete random variable takes on a fixed set of possible values with gaps in between. The probability distribution lists all the possible values, the x's, and their probabilities, the p's. So it will look like this. We have a list of x values and a corresponding list of probabilities. The probabilities must satisfy 2 requirements, and this shouldn't be anything new for us. Every probability must be between 0 and 1, and the sum of the probabilities have to be 1. We saw that in the previous section about probability. To find the probability of any event, we simply add the probabilities of all the different x's that make up the event. And let's get into some examples. So this problem, baby's health at birth, let's read where these numbers are coming from. Here we go. In 1952, take a minute, read this. It talks about what these Apgar numbers are, these Apgar values. Number from 0 to 10, it evaluates the baby's health. So we have a probability distribution, or at least we have a table of possible values and probabilities. The question we're being faced with is, show that this is a probability distribution. Show that that's a legitimate claim, where x is our value for our score. We're going to make a histogram, describe it, and then we're going to find a probability. So, is it legitimately a probability distribution? Yes, because all of the probabilities are between 0 and 1, and if we add up all of these numbers, they add to 1. So it is a probability distribution. We're going to make a histogram that has 11 bars, numbered 0 through 10, and their height will correspond to the probability. It will look something like this. First few bars very, very small, and then they get much larger as we get out here to 7, 8, 9, 10. Again, we center each bar on the data value, on the value for the random variable, because it is a single solitary value. And what we see is that this is left skewed. That's some old vocabulary for us. And what that suggests is that a randomly selected newborn will probably have a score at the high end of the scale. There's a small chance of getting the baby with a score of 5 or lower. or something along those lines. That's a good description of what we see. Now, how do we find this probability that x is greater than or equal to 7? Well, that's going to be the probability of getting a 7, an 8, a 9, or a 10. We add those numbers up. 0.099 plus 0.319 plus 0.437 plus 0.053, and we get 0.908. So if we're considering 7 or higher a healthy baby, we have a 91% chance of getting a healthy baby when it's born. Okay, so probabilities distribution, fine. We can make a histogram, fine. We can find probabilities, cool. But what about average? What about mean? What about standard deviation? Well, we're going to want to deal with SOCs, shape, center, spread, outliers. We're going to care about the mean. We want measures of center. So the mean of a random variable is the average of the possible outcomes. And each outcome is weighted by its probability. So if we have a probability distribution here, the mean or expected value of x, we multiply each value times its probability. Each value times its probability, and we add all of those up. That gives us our mean value, m sub x. Or we call it expected value of x, capital E parentheses x. It's the summation of xi times pi. So let's go back to our Apgar scores, find the mean of this random variable and interpret it. So pause the video right now and try to apply this formula. So here's our formula, let's go. 0 times 0.001, 1 times 0.006, so on and so on and so on. You should have ended up with 8.128, meaning that the mean score of a randomly selected newborn is 8.128. And that is the long-term average of many, remember long-term for probability, many randomly chosen babies. Expected value does not have to be one of our values from the data table. It can be a decimal. It's an average, guys, and that's okay. So you see, if you ever want some good humor, if you will, regarding statistics, regarding some mathematics, Dilbert is an excellent place to go. Here's a comment talking about expected value, and I hope that this is not, I repeat, not any of you during this course. None of this pretending to be dead. We will deal with our expected values. So standard deviation, whoa, this must be hard, right? No, not really, guys. We can do this. We calculate standard deviation and variance really the same way that we do for a list of data, except we have to weight each value by its probability. So it's the sum, the variance is going to be the sum of the difference between each data value and the mean squared, and then we multiply that by the probability. To get the standard deviation, we simply square root the variance. Old stuff, that's from way early on in this course. So here's our Apgar Scores table again. Let's find the standard deviation now. So go ahead and try to apply this formula that we just saw, which is right here. We find the variance, then we square root it. Difference of the data value and the mean squared times the probability. Difference of the data value and the mean squared times the probability. We do that with all of these. We get that the variance, sigma squared sub x, is 2.066. Therefore, the standard deviation, sigma x, is 1.437. We square root. And what that means is, on average, a randomly selected baby's score will differ from the mean of 8.128 by about 1.4 units. And that, ladies and gentlemen, is where we will stop for today. Coming up next are the continuous random variables. Think back to what we talked about earlier in the course about what continuous variables are.